Hi, welcome to this lecture. In previous lectures, we have seen that developments in the B method start from an abstract machine which can then be refined to refinement components. In this lecture, we will present a special sort of refinement component that constitutes the final refinement, implementation. Implementation components are a special sort of refinement that can be translated using Atelier B to source code. For that, we impose limits to the constructors and data types that can be used. Developments in the B method start from abstract machines. Based on project decisions, we can refine them by refining data structures, introducing algorithms, or reducing non-determinism. Usually, refinements will have proof obligations that need to be proved to guarantee the correctness of the refinement. Implementations constitute the last refinement and also produce proof obligations. They also differ from refinement components in the restricted subset of the B language they can use, constructors and data types. This restriction helps Atelier B to automatically generate source code from the implementation components. The language that can be used in the implementation is called B0. All details can be found in Atelier B's language reference manual. Here, we will simply summarize the restrictions. The static part of the implementation is related to the structure of the components and to their sets, constants, and state variables. We may use the following clauses: refines, which is mandatory, imports, sees, and promotes for structuring, sets and their properties, concrete variables and their invariant, concrete constants and their values. The dynamic part of the implementation is related to instructions that can be used within the initialization and operations. We may split this part into 5: B substitutions, B expressions, B predicates, B types, and B values. In the B0 substitutions, first we have the skip, which is a command that simply terminates and does nothing. We have assignments like XX receiving 10 or SS index 2 receiving 10. We have the sequence like XX receiving 10 and then YY receiving XX. We have alternation like the if then else we have here in the screen, in which if XX is greater than 0, then YY receives 1, else YY receives 2. But we will also have variations of this alternation. For example, we may have if then else's in which the else part is not relevant and we remove it from the command. We also have the case substitution. In the case substitution, we have here in this example, in which if XX is 0, then YY receives 1. Or if it's 1, then YY receives 0, else YY receives 10. In this command, if the value of XX matches the expression like 0 and 1, then the corresponding command will be executed. Otherwise, if the value of XX in that moment does not match any of the values, then we go to the else branch and YY receives 10. We also have loops in the implementations. And loops is a special subject which we will be dealing with in another lecture. So in this command, while the condition CC is true, we do the command S. And throughout the behavior of the loop, the invariant, the predicate P, is satisfied. And the variant E, which is an integer, a natural expression, must be reduced in every interaction. But as I said, we'll be dealing with this subject in another lecture. We can also have blocks, simply by starting the block with the begin keyword and finishing the block with the end keyword. And we also have variable blocks, like this variable block that we have in the screen, in which we declare the variable XX and we execute the command between the keywords in and end. So first, we initialize that variable, XX receive 10, and then we execute the command YY receiving XX. We may also have operation calls of imported machines. So if the implementation imports a machine, then we call the operation of that machine. And for that, we use less than hyphen hyphen. So it's like an arrow to the left in which we assign to XX the output of the operation OP by giving the input argument YY. We can also have operation calls, but read-only operation calls of machines that we see, implementation sees. So we can have read-only operation calls of seen machines. But structuring is also a subject of another lecture. It's very important to notice the difference between an assignment and an operation call. Notice here in the screen an assignment. It's XX receiving, so we have colon equals expression. So XX receives the value of that expression. But if we have an operation call, then XX left arrow OP and give the argument YY. So assignments using colon equals, and operation calls to assign to a variable, we use the left arrow. Regarding B expressions, we can have an identifier or literal constant like XX. We can have access to an element of an array like AA index XX. We can have the following arithmetic expressions: summation, E1 plus E2, difference, E1 minus E2, the inverse, minus E1. We can have the product of E1 by E2 and the division of E1 by E2. Finally, we can also have the mod, the E1 mod E2, which gives us the remainder of the division, the integer division of E1 by E2. Finally, we have the expression bool, and we give a predicate to that bool, which returns us a Boolean value. Regarding B predicates, we can have conjunction using commercial E, like B1 and B2, disjunction using B1 or B2, negation using the keyword not, so not B1, and we have the comparison of values in which a total order is defined, like for example integers and natural numbers. So we have equality, XX equals YY, inequality, XX difference of YY. We have greater than, we have greater or equal, less than, and less or equal. It's very important to notice that some expressions cannot be used in a condition, and that includes all the arithmetic expressions and the operation calls. So operation calls and arithmetic expressions cannot be used in a condition. For example, if we have the alternation if XX plus YY greater than 0, then XX receives 0, else YY receives 0, and that cannot be used because we have in the condition of the alternation arithmetic expressions. So the solution for that is to declare a local variable SS and initialize that variable with the value of the arithmetic expression XX plus YY. And then we use that variable in the condition. So our alternation becomes if SS greater than 0, then XX receives 0, else YY receives 0, and we close the block, the variable block, also with the end keyword. B0 types, we have scalar types like natural numbers, integers, but both we can only use the finite version. So we have nat, int, we have the booleans, bool, and we have the defined or enumerated sets. We can also have arrays, like these 3 examples here we have on the screen, in which XX can be an array defined as a function from T1 to T2, or for a pair T1 Cartesian product T2 to T3, or as a function of functions, so a function from T1 to a function from T2 to T3. Concrete variables can either be scalar or arrays, and concrete constants can be scalar, arrays, and also subsets, like for example defining xx as a subset of T1. Regarding B0 values, we have that concrete constants and defined sets have to be valued. So subsets, like for example my set equals 0.10 must be valued, as in this example. A scalar value, we use the equals to assign a value to that constant, to that scalar value. So cc, for example, cc equals 10. And an array can also be initialized, for example, as here in this example, where cc equals my set Cartesian product, the set containing 0. Now, let us move to an example. So our example is very simple. It's just to illustrate how do we value the sets. So our machine date field has 6 different sets: hour, minute, second, day, month, and year, and also has an enumerated set called mm with 2 elements in it, am and pm. Now, if we want to implement this machine, we can provide another machine, an implementation called date fields I that refines date fields, and then we use the clause values to define all the different sets. So we can say, for example, that hour is the set of numbers ranging from 0 to 23. Minute and second are sets of numbers ranging from 0 to 59. Day ranges from 1 to 31, month from 1 to 12, and year from 1900 to 2100. Now, using Atelier B, we can actually generate code. So we use the code generator, and we get the following code. We have a header file, a header C file, in which we define the maximum values for all the different sets. We differ the types for the sets. We have enumerations for the enumerated sets, and as we can see, we don't have any concrete variables, and we don't have any concrete constants as well. And the C code is actually empty, almost empty, because we don't have any operations in it, so the initialization is void and does nothing. So actually what we have here is the definition of the deferred sets. And this concludes the example of the date fields. As a final example, let us present a machine that registers the goods purchased by a given customer. It contains a set of goods that can be purchased, a set of goods that have been purchased, a table that gives us the price of each good, and a table that gives us the price limit that the customer is willing to pay for each good. In this machine we have 3 operations. We can buy a good which price is below the customer limit. We can set the price of a good, and finally we can query the price of a good. Let's go. So let's see the machine customer. The machine customer has 3 variables. It has the purchases, the limit, so that limits the price, that gives the price limit for every good, and a function price that gives us the price of every good. So we have a deferred set called goods, and in the invariant we declare purchases to be a subset of these goods, the limit to be a function, a total function from goods to natural numbers greater than 0, so every good must have a price limit, and price that gives price, so it's also a function from a total function from goods to natural numbers greater than 0. We initialize the purchase with the empty set, and we also initialize limit and price as one of the possibilities. So we declare limit to be a random function from goods to natural numbers, and price also to be a random number. So we use this assignment which give us an element of the set of all functions from goods to natural numbers. So that assigns to price a random price table. So in the operations we have buy, set price, and price query. So to buy a good, you give a good to these operations, but this good has to be within the price limit for that for this customer. So the price of GG must be less or equal to the limit of GG. And if that's the case, we include the goods, the good in the purchase using the union, and we give as output, so we assign to PP, our output variable here, we assign to PP the price of GG. To set a price, it's quite simple. We get a good and natural number greater than 0, and we say that assign to price of GG the given price PP. Finally, to query a price, we simply give a good, so price query receives a good GG, and gives as output, so we assign to the output variable PP the price of GG. So if you animate that in Pro-B, let's initialize using, for example, this constants here. So you have that limit of goods 1, 2, 3, 4, and 5 equals 1, and the price of 1, 2, 3, 4, and 5 is 1, 2, 3, and 4 is 1, and the price of the goods 5 is 4. So as we see here, we can buy good 1, 2, 3, and 4, but we cannot buy the goods 5, because the goods 5 price is 4, which is greater than the price limit 1. So let's say we buy good 1, good 2, good 3, and good 4. So see here, our purchase contains all the 4 elements we have just bought. But now let's say we want to set the price of goods 5 to 1. Goods 5 to 1. And now we are able to buy that good, because now the price of goods 5 is within the limit. And we also have here, we can also operations to set the price and the price query. So the idea now is to refine this machine using an implementation component. So we have here the implementation customer I, which refines customer. It also has a variables limit. So here we are declaring that these variables are concrete. So we say that we have concrete variables limit, price I, and purchases I. Limit is still a function, so that will give us a total function from goods to natural numbers. Price I also a total function, and it actually is equal the abstract component. And purchase I is now, which was a set in the abstract machine, is now declared as a total function from goods to Boolean. So the idea here is that a good is mapped to true if it is in the abstract set purchases. So if we get the concrete function, if we get this function here and make a range restriction on the set containing true, that will give us the functions, the pairs in which the second element is true. If we get the domain of this function, this will give us all the goods that are mapped to true. So this gives us all the goods that were purchased, and this equals our abstract set purchases. We also have here to value the deferred set goods. So here we are saying that goods is the set containing all numbers ranging from 0 to 10, all natural numbers ranging from 0 to 10. So in the initialization now, we can actually, in the implementation, initialize arrays like that, where the left-hand side of the Cartesian product is the set of indexes. And so our limit is the Cartesian product of the set goods with the set containing 10. So this is actually saying that all goods have a price limit of 10. And let's say we initialize the price I with this Cartesian product, which maps as a return, returns a mapping from all goods to the number 1. So we're actually saying that initially the price of all the goods is 1. And let's also initialize purchase. We're using a Cartesian product, but this time we're mapping all the goods to the value false. So this is actually saying that our abstract set purchases is the empty set. So by mapping all goods to false, we're saying that no goods were purchased yet. Now let's see how we implement the operations. So to buy a good, we give as output the PP the price I of GG, and now we have to check if that price is within the limit, the price limit. So the idea here is to have a comparison of the price with the limit, the price limit of that good. However, we cannot use limit of GG here. What we have to do is to declare a temporary variable and assign to that temporary variable the value of limit of GG, and then we use an if-then here, an alternation to check if PP, if the price we checked is less or equal to the temporary value. If that's the case, then we make the purchase. So how we do that? We assign purchase I of GG, we assign the value true. So we're basically mapping GG to true. The other two operations are quite simple. So we have here set price of GG at PP. What we do, we simply assign to price I of GG the value PP. So we map GG to the price PP, and the price query assigns to PP the output value, the value of the function price I on the good GG. So we assign to PP price I of GG. And we are now able to generate code as well here. So we generate code here. We generate the C code, and what we have here is also a header, which simply is declaring the constants and the signature of the operations. And we have the C code that was generated for that machine. So we have arrays. So the customer limit is implemented now as an array. Customer price E, the price I is also declared as an array of 11 elements. So from ranging from 0 indexes, ranging from 0 to 10. And just one thing here, notice that the name of the components, for example limit, is preceded by the name of the machine, and this is happens with all the components. So in our initialization, we have 3 loops, one to initialize each of the arrays. So we have a loop that initializes all values, all elements of the array limit to 10. We have a loop that initializes all elements of the array price I with 1. And we have a loop to initialize all elements of the array purchase I with the value false. Now we have the 3 operations here. We have the buy operation, which gives us output. So here, in order to be able to have more than one value returned, what the translated code does is to use pointers. So we have pointers here. We pass a pointer as an argument of the function, and we assign to that variable the value of the output. Then we have the temporary variable here, which receives the value of the return of the value of the element GG in the array limit, and if that value is less or equal to temp, then we assign true to the element GG of purchase I. The other two functions are quite simple. So to set the price, we simply assign PP to the element GG of the array price I, and the price query simply assigns to the variable that was given as input here as an argument to the address, to the pointer, we simply assign it the price I of GG. So you can actually, for this lecture I have prepared just a very small main file. So we simply initialize the machine, so we invoke the initialization of the customer. We will set the price of the good 1 to 9, and as we saw, the price limit is 10, so we can actually buy that good, the good 1. So let's buy good 1, and let's use the address of PP as an argument to get a return. So we will get on PP the price of that good, and actually we will print that out. So we can now compile this file, and as we can see here, when we executed the executable file that was created in this compilation process, we start the execution, and then we do get 9 as an answer. And that completes the example of the development of the customer machine. And that's all for today. See you in the next lecture. Bye.